There. Finally, I got it right, and we will go. So good afternoon, ladies and gentlemen of SCG in Argentina, and thanks again for the invitation to be able to talk today. For those that are online, it would be good to mute yourself, otherwise my video will stop. And so if you mute yourself, it'll be easier for the recording. I just wanted to point out today that we actually, this is international IAGOD Distinguished Lectureship associated with SEG, but also IAGOD, International Association of the Genesis of Ore Deposits. And I'm going to just switch over to my laser pointer. Our next big meeting will be in Dublin in 2022. And actually, Salta in Argentina was the host to the 2018 meeting that was very well received and was an intricate part of the IAGOD quadrennial symposiums. So if you're doing research, in Argentina and you want to present, definitely consider that meeting. IAGOD actually has student members as well. That is a free membership, and so consider joining IAGOD. We tend to serve do different things than SEG specifically, and kind of there's a synergetic relationship between IAGOD, SGA, and SEG. One of the things that we do have for full members is obviously we're part of Ore Geology Reviews, of which I'm an associate editor. We also are a member of Elements magazine. And then we have a lot of different types of things like special volumes, working groups on different deposits, and so on. So I just thought I'd introduce IAGOD and mention that so that you can consider that in the future for yourselves. Okay, so today I'm going to give a very general lecture associated with fractionating igneous systems. And some of these igneous systems as well include some that are in Argentina that I've happened to see. The specific ones relate to actually some of the igneous systems that we have specifically in New Brunswick, but many places around the world. And looking at these fractionated igneous systems actually is kind of useful for the study of many rare metal type and critical metal type deposits. This one here is more focused at tin, tungsten, molybdenum type deposits. Though, so now this here is a view of Thor Lake T-zone, which is one of the largest. This here is a pegmatite, probably the most complex pegmatite system in the world. It's actually a peralkalic pegmatite, and it's an injection out of the extremely large Nechalacho heavy rare earth yttrium deposit in the Northwest Territories, which is associated with a plume event at 2.3 billion years ago. Fascinating place, and it's the gentlemen here are both the world leaders in heavy rare earth deposits in the world. So the premise of this talk is that there is presently really no reasonable mechanism recognized to produce ore deposits extremely rich in incompatible elements. So therefore, volatiles are commonly invoked to enhance the abundance of these metals within these types of ore deposits. Rarely is extreme or hypercrystal fractionation, or specifically hypercrystal fractionation, invoked as a mechanism due to the very low temperatures of these magmas, the relatively high viscosities, and actually very high viscosities of these melts, and then the minimal density difference between minerals like quartz and the associated felsic magma. So the overall magma systems are not conducive to what we would normally think would be crystal fractionation like we would know in many other systems. And then there are also some other considerations, like the thermal limitations, excuse me, of some of these magmas, i.e. the size of them is not like the Bushveld complex or some other large igneous systems. Now, this all came about when I was reviewing some papers. Obviously, I do that a lot. And also one of my best friends, Richard Ernst, he is one of the leaders in LIP studies in the world, large igneous provinces. And we were talking over beers, and I said, you know, Richard, why hasn't anybody talked about the thermal limitations associated with the generation of ore deposits in silicic large igneous province, or what we call slips? And he said, well, Dave, nobody's thought about that. Nobody's written about that. And this is back in 2012 at a bar. And in the end, Richard Ernst invited me to be a keynote lecturer in Hanoi, Vietnam, at a LIPS conference he was organizing. And so this is the derivative talk related to that. So it's a real problem. One of the problems ends up being is that, like I said, because people haven't really discussed or tried to attack what is the mechanisms to cause the enrichment of these systems to very high levels of silica and so on, they commonly will invoke these hydrothermal processes. And this is a classic paper related to this issue. And so, for example, the niobium tantalum fractionation associated with some paraluminous granites are used as an example. So in order to get the niobium tantalum ratio down to very low levels, enrich the magma with tantalum, like lithium, cesium, tantalum pegmatites, they commonly will see this break here and relate that to a hydrothermal process to drive fractionation up to ore grade levels of tantalum associated with some of those pegmatites. Similarly, we see that for tin, where to get high enrichments of tin, they commonly will invoke hydrothermal fluids or that magmatic hydrothermal transition instead of looking at fractionation. And so they've come up with this diagram to indicate areas where hydrothermal fluids are dominating the fractionation array at very low niobium tantalum values and very low zirconium hafnium values. So they're inferring that hydrothermal zirconium and hafnium and hydrothermal niobium and tantalum are associated with some of these very enriched magmatic systems. My point is that they really didn't fully try to explain this. They just noticed the chemical differences. So my point right off the bat is that we know that some of these are actually fractionated magmas. And the reason is for just two examples, and there's other examples as well. So the Macusani tuff in Peru has near ore grades of beryllium, tin, tungsten, tantalum, niobium, rubidium, and so on. And it was actually looked at to actually mine for uranium by Cameco. It's highly paraluminous, but it's a tuff. And the tuff actually represents an air fall tuff that is a glass shard, bunch of glass shards. So the gas is not part of the glass shards, which are crystalline or quenched melt shards. So therefore, there's no hydrothermal enrichment. This is a melt that is actually enriched in these elements. Then we also have on the other end member, for peralkaline systems, we have the niobium tuff in Western Australia, also called the Brockman tuff, very famous. And again, we have near ore grades of niobium, tantalum, rare earths, heavy rare earths, yttrium, zirconium, hafnium, just like a peralkaline pegmatitic rock, like an NYF pegmatite. So now it is recognized that the solubility of the minerals hosting incompatible elements can be very high, such that they can crystallize as phenocrysts and therefore are not only enriched by magmatic hydrothermal processes, i.e., we can fractionate these melts without the exsolution of a hydrothermal fluid to enrich them to these values. So how do we do that? That's the question. So let's stand back. Okay, this is the table that Richard Ernst, he looks after this website, and you can see Richard Ernst's name is on some of these classifications that are down here. He's really the preeminent LIPS expert in the world. He's a good friend of mine. We used to share an office together. Yeah, very nice guy, and extremely famous for his work on LIPS. And silicic large igneous provinces, or SLIPs, are associated with greissenite, tin tungsten deposits associated with some granites and so on. And therefore, this is why I'd asked Richard the question, why hasn't anybody talked about why some of these magmas are enriched in these systems? So here's just an illustration of some large igneous provinces. This is a summary from Franco Paragino's work, where we can see variable sized mafic to felsic magmas within an overall crustal regime. But one of the things that you immediately recognize is that they all are different sizes, and they all actually have different levels of fractionation, some of which are A-type granitic rocks or other supercrustal type rocks. So key points to get to are the size matters in forming magmatic ore deposits of sufficient grade and abundance. So size matters. This is important. Smaller felsic magmatic systems are more susceptible to their host environment than our large mafic magma systems, as viscosity, diffusivity, and mineral differential density are key in crystal melt separation, like we normally think of when we crystal fractionate a magma. And therefore, for large mafic systems, separating a mineral like olivine or clinopyroxene or something from the melt is not near as much of an issue, because the mineral densities tend to be higher. Then the temperature difference between the minerals liquidi are much different in a mafic system versus intermediate and felsic systems. So felsic systems, the liquidi between quartz felspars on a ternary diagram, or the cotectics, are very small relative to each other, and so differential settling and fractionation is more of a problem. So here are just some examples of various enriched LCT type pegmatite systems and associated niobium yttrium pegmatites and so on around the world, several of which actually occur in Argentina here. My laser is moving very slowly, as well as obviously the famous ones associated in Brazil. And of course, we have quite a few here in Canada, especially Tanco, which is one of the most famous LCT pegmatites in the world that was mined for those types of features. So let's just take a look at what these magma systems look like. Here's a diagram done by David Strong from 1983. Here, pressure going at depth, temperature increasing this way. This is the general solidus for the granite system. And this here dashed line is the modified granitic solidus. Notice it's depressed to lower temperatures here as we add beryllium, boron, lithium, phosphorus, fluorine. We lower that solidus. So there's a difference between the granite solidus and the modified fluorine-boron-rich solidus that allows fractionation from here to here in highly silicic systems. And this obviously is looking at granites in compressional settings where they actually move up a thermal gradient towards their emplacement depths. So this is well-known stuff. But in order to do that, we need time. I'll skip over this, but the important thing is we're really looking at tin-rich systems here as an example of one of those systems. And the pegmatite classes that we see represent different sources as well as degrees of fractionation of those melt systems towards ore levels for the peralkaline pegmatites or the lithium cesium pegmatites, or even just hypabyssal granites that have tin, molybdenum, and so on. So they can fractionate right through to very, very low temperatures here in this environment. And what do those two solidi look like? This is again the solidus for a normal granite, and then this is the solidus for a fluorine boron modified granite here. And so things can fractionate further down to lower temperatures in order to enrich those melts further in those elements. Now, they're going to lower temperatures, but how do they do that? How do they fractionate through when the solidus is being modified by fluorine, boron, lithium, and so on during that fractionation? Chemically, we're looking at mineralized systems that actually have generally very high silica, tin being enriched above silica values of 73, 74% in order to get these magma systems enriched in enough tin or those other elements that I'd mentioned. And what are some of the other indices? Well, we can see that when we actually have magma systems that are fractionating, they can fractionate along these vectors to enrich themselves in some of these elements. Now, I'm just showing this on a diagram that's been popularized by Pierce et al. 1984 and modified by Christensen and Keith 1996. So what do these things look like? Well, some of these magmatic systems actually are, like I had noted, crystallizing phenocrysts of ore minerals. Now, I mentioned the Macusani tuff, I mentioned the niobium tuff, but we actually have pegmatites that have crystallized molybdenite within the pegmatite. Here's just an example. Uranonites in pegmatites, like the ones I studied, cassiterite in pegmatites, even wolframite and scheelite in pegmatites, of course, tantalite in pegmatites, and then various types of gem beryl and pegmatites are just some examples of minerals crystallizing as phenocrysts in those evolved felsic magmas. Here's just an example of some of the pegmatites I've studied and seen. This one here includes an andradite crystal that is actually, partially radioactive. And here's a very large allanite crystal. And many of you have seen these types of pegmatites that are enriched in rare earths, this one here being light rare earth element enriched, and then it's metamict around that. So obviously minerals are coarse, they're growing at low temperature. This pegmatite probably crystallized at around 630 degrees. So how are they related? Well, the pegmatite systems and the hypabyssal part of the granitoid system is here. And then as they crystallize inward, they can shoot off pegmatite aplite dikes or brachodiatremes and so on. But also, eventually, many of them will become water saturated and partition elements like tin into those hydrothermal fluids. The main point here, though, is that they can be very fractionated to that stage. So here's just an example of, here's a differentiated peralkaline rhyolite from the Azores that Jim Mungo wrote about back in 1996, just as an example. So extreme fractionation, how are they happening? And then he compared it to Strange Lake, which is one of our other large heavy rare earth yttrium, niobium, zirconium pegmatites in Canada, one of the largest in the world. And there's an example. Here's an example done by Jackson in 1985 of the various types of deposits associated with peralkalic systems that are enriched in yttrium, heavy rare earths, and niobium, zirconium, etc. And again, notice very similar. We have brachydiotriums, we have contact Stockscheider-like pegmatites, endogranitic pegmatites, and other offshoot pegmatite dikes associated with them. This example was the one of the largest heavy rare earth deposit in the world, called Guraya in Saudi Arabia. And there's another example of what they actually look like. Well, these things crystallize at many different levels, and their hydrothermal systems look different as we move into the upper parts of these systems. But generally speaking, these upper level parts of the cupolas are enriched to the point where they can generate these deposits. And here's an example of what some of them look like. This one is from Dave London, where we have granites, fractionating magmas going out. What do they look like? They're enriched in a bunch of elements that are very incompatible, low temperature. But again, we have the issue is, how is that doing that? Is it doing it hydrothermally, or is it doing it via igneous processes? So I want to step back one moment to talk about an older paper that was done, reminding people that the source of these magmas, in the case of tin deposits, and Bernd Lehmann actually worked a lot, obviously in Germany, but also in Bolivia, the famous Bolivian tin deposits that you might know about, that extend down and into northern Argentina, which is why I'm using tin as an example, tin-silver association, like Periquitas and so on, is that those magmas are from supercrustal rocks that are somewhat enriched in tin. So we're not starting out with things that are like mantle compositions, we're starting out with the right melts. But then how do we fractionate those through to make ore deposits? Here is a recent paper just done by Bernd Lehmann in Lithos, where he describes exactly the same thing with the enhancement of understanding of the tin going from bulk compositions of tin in and around this area and fractionating them up to, in essence, more magmatic types of deposits. And you can see the sketch from that paper talking about Stockscheider, pegmatites, and so on that are quite enriched in tin from the original source area, but fractionated through to actually create very tin-rich magmas, just as the example I showed. So one of the things that really got people thinking about this, just like I showed earlier with the ores of molybdenite, uraninite, and so on in fractionated magmas, the actual phenocrysts, this was noted again by a guy that I know very well, Rob Linnon. Rob actually, as part of his PhD thesis, recognized magmatic cassiterite crystallizing out of these aplites and pegmatites. So magmatic cassiterite was important to those magmas and therefore had to enrich itself in order to actually crystallize out, i.e. it's not hydrothermally enriched. So he went on to actually do experiments where they would put a cassiterite crystal in a melt, heat it up, and dissolve it in that melt to see how enriched those melts would be in tin. And they measured, they have just on here, what's the solubility of tin on this axis and this axis. And then they looked at it relative to temperature. Now, all ore minerals will dissolve more at higher temperatures. However, we're talking about the enrichment of magmas to higher and higher degrees towards lower temperatures until they saturate in cassiterite. And so we're most interested in these solubility experiments here. And you can see that here in this melt, they can have about between 2,000 and 3,000 parts per million tin dissolved in the melt at 600-700 degrees. That's a lot of tin dissolved in that melt based on dissolving a cassiterite crystal in the melt. Now, this was done by Bala in 2005, which was redone from Bob Linnen's earlier experiments, and Bob Linnen was a co-author and the lead author on this. They did further work on tin here and showing that at very reduced composition, at very reduced fugacities of oxygen, that the tin could even be higher than that. And they used higher temperatures here. So this was done at 850 degrees, which isn't really realistic for our purposes, but it shows that as we change the periluminosity, i.e. how much normative corundum the melt has, that tin goes up. So periluminous magmas can dissolve a lot more tin if they than the haplogranite magmas. And so here's just an example of this where we can actually do this and enrich tin in some of these magmas at low oxygen fugacity at relatively low temperature up to almost 3% tin. So that was going from the earlier one with the haplogranite at 700 at 0.3% tin all the way up to almost well over 1% tin dissolved in the magma. So we know that that can happen based on the solubility of cassiterite in the melt that is measured by those studies. And they've done this as well for tantalum, beryllium, and so on, as well as other minerals of interest. So we know that. What's the other example? Well, one is what is the solubility of uranium in these type of melts? And we can also see that uraninite can be dissolved in these magmas as well, as I had shown back in the mid-1990s. And here's just an example of that, and then looking at partition coefficients for that. Okay, let's back up for a second. Now, I'd said that it takes time in order to crystallize magmatic systems. And this is one of the first ones. And notice I had said to Richard Ernst back in 2012, I said, you know, very few people have talked about how magma systems cool and how they fractionate. And here's one of the early ones that looks at the distribution of heat within a magma system that's fractionating, looking at that fraction of melt. So this paper showed up in Geology right after that. Here's another one. This was done by Hawksworth, where he was actually dating, that group was dating magmas that were differentiating through a temperature range. And you can see here that with fractionation, that the differentiation took on the order for this magma to evolve to high silica aluminum concentrations. It actually took almost 250,000 years, which was based on the isotopes that were done, helium isotopes that were done on this magma in order to figure out how long it took to fractionate. And you can see this is in essence, 250,000 years here to fractionate through to high concentrations of zirconium, high concentrations of silica aluminum, like we know. So it takes time. Other ones that have come out more recently, this one here is just out a few years ago, actually use normal uranium lead dating of various magmatic systems in an area to talk about what is the life of a normal fractionating magmatic system. And you can see here that the geochronology of this system shows that all of these intrusions in this one area, now there's no deposits associated with it, but it shows that it's differentiating only on the order of 1 million years for an interrelated magmatic system. And therefore, that's an important constraint on this. Now, we've been involved in several publications now where we're looking at similar things associated with ore deposits. Okay, so fractional crystallization near eutectics is very important. So this is the quartz albite orthoclase ternary diagram. And this is the eutectic in that system going from deep levels to shallow levels. And this is one that I looked at for my PhD way back. And you can see on this diagram, temperature versus water, that it's fractionating down through crystallizing out plagioclase, quartz, and then it has some volatile exsolution associated with that. So key here is fluxes lower that solidus to low values, but we have the issues of decreasing diffusivity of various elements in those highly polymerized silicic magmas. Then we have, again, that challenge crystal melt equilibria and minimal density differences between minerals and melt. And therefore, how do we crystal separate? How do we enrich these magmas? Obviously, I mentioned about the fluxes involved. If we take a melt here at any one temperature at, say, 1 kilobar or 2 kilobar, as we add boron or fluorine, they depress that solidus significantly and allow it to crystallize to low temperature. So I just wanted to mention that to you again. All right, so getting back to a specific magma system that would be enriched, like Bernd Lehmann had talked about. So the source here might be enriched on the order of 10 ppm, which is typical of many supracrustal type rocks, which is what Bernd Lehmann had indicated. And if we actually did some partial melting of that, based on the partition coefficient that we knew for tin in partial melts, we can enrich that about 7-fold at about 5% partial melt. You can do lower degree partial melts. 3% is needed to get melts to move in deep crustal zones. Here we just used the example of 5% partial melting at the partition coefficient of tin into the melt of around 0.1. So that can enrich that melt about 7 times. So if we have it about 7 times, that makes this 10 ppm about 70 ppm. So that's for batch melting with a D value of 0.1. So it's getting enriched in the melt quite a bit by doing that. Then we go over to Rayleigh fractionation and we start separating out crystals that don't have tin in them relatively, and that partition coefficient can be as high as 0.1 or 0.01 here. And so the fraction, as we take this melt and we fractionate this melt, this can enrich this system further so that we can enrich 10 to 20 times the amount of tin. So if we enriched it 20 times to about 4% of the melt remaining, we get 20 times 10 ppm equals 200 ppm. And if we take that, and so 100 to 200 ppm here times 70 equals 1,000 to about 7,000 ppm based on Rayleigh fractionation. So all of a sudden, the mineral solubility data that Bob Linden had come up with and his students actually is coincident with how we can actually fractionate these magma systems. So we can do that through the normal model of understanding partition coefficient by partial melting in the source, as well as mobilizing those melts up and fractionating them all the way through to very high levels where we can enrich them up to well above 1,000 parts per million in those melts. So where does that occur? Because we don't see that everywhere. And so I wanted to take you to the Bushveld complex, which is obviously an important region, and we have deposits there associated with tin. Now, the Bushveld complex, as you can see here, is around 2.08 billion years old. This is a summary from Brian and Richard Ernst back in 2008 that I wanted to point out. And one of the big tin deposits in the world is associated with a granite that intrudes in through the Bushveld complex. So the Bushveld complex came in, it crystallized, and then some magma systems intruded through that Bushveld complex. And this Zyplatz tin system is one of the fractionated magmatic systems that intruded through the Bushveld complex and enriched the granite up here to ore grades in the granite and pegmatite. Oh, and I wanted to point out that the age of the granite and the age of the, this is the age that they noted for the Bushveld, the age of the granite that intrudes the Bushveld is 2054 million years old. So it's intruding right after the Bushveld, which is the largest igneous system there is on the planet, are almost the same. And the temperature and pressure of crystallization is there as well. Here's another deposit. This is a heavy rare earth deposit that was published on, and the geochronology of that heavy rare earth deposit is actually located here. And it's also almost the same age as the Bushveld. So the Bushveld, in essence, is here, and the granites intrude after the Bushveld complex. So here is Dave Groves and McCarthy from 1978. This is how they looked at the development of the Zyplatz tin deposit associated with granites in the Bushveld, and the granites themselves, how they crystallized. And this is how they illustrated that by this crystallization model, which is called a solidification front crystallization model, or a boundary layer differentiation model. And you can see how they crystallize inward into pockets, and then from those pockets, they're enriched and form those pegmatitic sheets associated with that pegmatite. So in essence, they're crystallizing inward to enrich themselves in tin. And then from here, they actually talked about what is the percentage of separation of minerals from the melt to enrich those pegmatites. And you can see here that if they have perfect separation, they could have enrichment factors on the order of 20 times, which is like I showed with that fractional crystallization model, the Rayleigh fractionation model. Is it possible? They knew at this time that that was problematic because of how the system crystallizes and the issues that I'd mentioned earlier. So here's just a thermal model. This is actually done by Bruce Marsh. And this is one that I had done for a series of dikes here in New Brunswick, where we have a fair-sized intrusion, and then it cools inward. And as it does, it can eject off dikes into the host rock. And the most fractionated dikes would represent the most fractionated end member here and in essence inject off. And so out of all these dikes at this erosional level, these dikes would be the most fractionated. So that's the point. That's a solidification front model. So how do we do that? So the important thing is, how do we allow that to fractionate through like that? Why are these magmas so rare? So here's an example where I used Heat 3D by Ken Wurlitz. This is the thermal gradient on the bottom. This is freeware, by the way. It's Kware. If you want to download it, it's free. And that thermal zone is here. This is in kilometers. So this is the crust mantle boundary here. And this is a normal thermal gradient in this region. Here's a magma that has input into this crust. And here I have dimensions of 40 kilometers just for this purpose of this explanation. And here it's at 1500 degrees, so it looks orange down here. And if we cool that large body down, now this is not like a silicic magma, it's more like a mafic magma, but if we cool it down until it's solidified, it takes about 500,000 years to crystallize to 1000 degrees. And you can see that labeled here. And all the rest is solidified because it is intruded into the upper crust and then cools. And this would be the solidus for the plagiogabbro or plagiogranite system. So it took about 500,000 years to do that. And if we cool it continually to the point where it actually cools down in this region here, where we're at between 800 and 600 degrees, that takes about 3 million years. So this size of intrusion cools to the range of what can allow a pegmatite to do over 3 million years to change this thermal gradient to something like this. So imagine what the Bushveld could do if it was that big. Here's a normal granite, which is 20 kilometers in diameter here. This here actually is several kilometers thick. I have it around 3 kilometers thick, and I intrude it at 800 degrees, which is, it's pink here, but it's supposed to be 800 degrees. And if I take that, this is the normal dimension of a hypabyssal granitic system, and I cool that to 600 degrees, below 600. So that's actually around 600, 650 in the middle, going around here. So that cools down that size of intrusion, 20 kilometers in diameter, about 100,000 years for it to cool. So small intrusions cool very, very quickly. However, if that intrusion intruded into the rocks that we had before that had just cooled to their solidus of 1,000 degrees, like this, at 1,000 degrees, if we intrude this magma into these hard rocks that are 300 degrees, how long will it take for this part, which is the same as this, how long will that take to cool? So here's what it takes for this to cool to 600 degrees now. Remember, it was 100,000 years. Now it is 1 million years. So by having this intrusion of granite intrude through a pre-existing hot rock, we actually have slowed its cooling, which can enhance its crystal fractionation. So we have 10 times more time for that to intrude and cool so that we can enrich that. Now, this actually was done for the Bushveld complex and the associated granite. Lawrence Robb, who wrote the famous textbook that I use in my class, ore forming processes. He did this for the Bushveld to look at the age of the intrusions versus the age of mineralization. And he came up with similar ages that temperatures that I had on the order of 4 million years to cool the Bushveld down to well below solidus temperatures. So in essence, normal granites are being extended by almost 30 times the cooling age. So with the solidification front or boundary layer differentiation model, we now have added with heat, we've added where we can take greater perfect crystal liquid separation with the bulk D values that I talked about, and those take time to actually allow for greater perfect fractionation. Also, if we have a lot more time, 10 or 30 times more time for felsic magmas to crystallize, we have better diffusion to those crystals to form bigger crystals and have less disequilibrium partitioning, which takes also time. And then that's external thermal energy from the pre-existing host rock having a different thermal structure allows that better crystal liquid separation to very low temperature silicic systems or fractionation of those magmas to produce those pegmatites. Those all take time as well. So to have these magmas fractionate to higher abundances of tin, molybdenum, tungsten, sometimes niobium, tantalum, and so on to ore grades, it just takes a lot more time. And that the purpose of this is to say that I think that we need to look at the fractionation of these magmatic systems collectively and not just one magmatic system in an area. And we need to actually date all magmatic systems and do thermal models to constrain the time of those fractionation. And we can do that. This has been shown to be able to be done by looking at crystal zoning development and so on. And so I just wanted to end on that to show that, yes, we have the time, we have the energy to do this, and we actually can extend fractional crystallization by understanding more the thermal environment in which these magma systems have intruded, and it is possible to fractionate them through to ore grade levels without the involvement of a hydrothermal fluid. Although hydrothermal fluids are key because it allows fluids from great depths to actually concentrate metals into the contact zones in the cupolas and carapaces of these magmatic systems. And so that's where the role of hydrothermal fluids becomes extremely important. So that's it. Thank you.
Thank you very much.
Very much, Dave. Very interesting talk.
Very interesting. Thank you.
Thank you. I'm sorry for the technical problems. I have a question. There is a modeling or similar modeling done for molybdenum-rich porphyry deposits, or using this type of modeling?
Not to my knowledge, although I have, well, they're not thermal modeling. We have done dating on some of the big molybdenum porphyries in Northeast China. We published that in International Journal of Earth Sciences in 2017. And just like the paper in geology, what we did is we dated all phases in and around this molybdenum porphyry, the pre-intrusions and the post-intrusions, and they all came out to be within 2 million years. A whole diversity of intrusions. And so in that case, you know, I was making the case, and it's noted in the paper that the thermal environment may have been conducive to allowing extreme fractionation, because you're right, molybdenum porphyries are only associated with very high silica granites, and therefore it's important to have those enrichments. Also, I just had a student here who was playing with this, working on another moly porphyry system, and he was playing with those as well. He was a visiting PhD student, kind of like yourself, but he was here a long time during COVID. So he got about as much as you did in 2 weeks in a whole year because of COVID, unfortunately. But he did some thermal models related to that, but they're not published. But it is, you know, these environments, as you know, molybdenum porphyries are in many areas of the world, and advective heat transfer is very important. Using the K-Ware Heat 3D is very easy. And so one of the things that I've suggested to others is that you can actually produce general models of rocks in your area and actually create a better thermal model for when the porphyry is being emplaced at depth within your specific region, to get an idea, is there a way to have an enhanced thermal gradient in which that magma can fractionate?
Okay.
So it's testable. And then also our uranium lead techniques with the triple quad and multi-collectors is such that we can start constraining these things in terms of geochronology to within 1 million years, plus or minus 1 million years, which then is modelable. So it's these are testable ideas, although in 3 dimensions, we really don't know how big some magmatic systems are. And so that is always going to be speculative, but I think it's definitely testable. The other place that I did some, as you know, I have quite a few students in Iran and from Iran, and we did a really neat study of a pegmatite in Iran associated with a normal calcalkaline granite, and it was a beryllium pegmatite that intruded calcalkaline intrusions and so on. And it actually came out to be exactly the same age as those rocks, and it wasn't xenocristic. Nice growth zones of the zircons in the pegmatites, and lo and behold, it had the same age. So I think we can test a lot more of these with high precision geochronology, and then also some thermal modeling. In that case, because it was a fairly large calcalkaline igneous intrusion, we knew that the thermal regime for that pegmatite crystallization, which is obviously coming in after the solidification, but right after, was actually from injecting at depth. That was also published in International Journal of Earth Sciences.
Excellent, Dave. We have some questions in the chat.
You can ask them. They can unmute themselves and ask them if they want. I think some are in Spanish, so I don't know if I can read them.
No, there are no questions, but we can ask if someone has a question. ¿Alguno tiene alguna consulta, alguna pregunta para hacerle a David? Puede ser en español y alguien va a tratar de traducirla. Si quieren hacer alguna pregunta o escribirla, pueden escribirla en español también y la traducimos. Así aprovechamos.
Well, thanks for inviting me. I very much appreciate that. Hopefully, we will see you in Dublin. All of you.
Yeah, would be nice to go. Yeah. Dave, another question. When you talked about the Bushveld complex,
Yeah.
you were talking about the tin deposits related with the granites.
Yeah.
But in the upper part of the ultramafic complex, there is tin in the magnetite. Linked to the magnetite.
Yes.
There is a connection between the...
Not to our knowledge. I think that's just part of, so when the Bushveld complex intruded, it intruded through supercrustal rocks, as you know. And so I think the melt system enriched itself in some of those incompatible elements. Also, as you know, the enrichment as they fractionate through to produce the magnetites at the top would then partition some of that in. But the granites, some of them are cogenetic, but most of them are intruding through the Bushveld from underneath and cutting through. Just after it solidified. It actually when it was an intrusion, a real active magma chamber, no magmas can inject through that. They can inject into it, but not through it. And so it was just after it solidified that the other melts could inject up and through, such that we can see them now. And they would be immediately after it solidified. So they cooled within that modified thermal regime. And I think that actually is much more common than people think, because you have all that advective heat coming from the mantle through that thickened part of the Neoproterozoic crust, and that heat is aiding melting of that whole crust. Then obviously when it solidifies in the upper part of the crust, soon as it solidifies, the rest of those melt systems can then fracture, migrate, and intrude into and above that Bushveld complex. So it's that thermal regime, in essence, the modified thermal gradient, which those magmas intrude, crystallize, and fractionate within. However, the important part of that is that, you know, that modified thermal temperature gradient is very rarely ever looked at as a controlling factor in magma crystallization. It's actually not even mentioned almost ever, which was why Richard had asked me to talk about that. Now it's like 7 years ago, but anyway.
Very nice.
So it's a very simple way of looking at these, and it's an easy one to use. Kware is free. Ken Warlitz has made all this stuff free, and it's fairly easy to use that thermal modeling program. You can, I actually have some videos to use that run that, because it is actually a video that it creates, and you have to take, and it stops every interval at certain intervals that you set, and I can take a screen grab of that, or I can play the video. Except whenever I did the video in the past, it would fail. So went in a talk, so I didn't use it anymore. But you can see how magmas crystallize into their thermal center, and as such, then understand the fractionation. My original use was like that original diagram I showed, where I used the dikes to show how dikes injecting off of a fractionating magma could get enriched. And it actually forms a peralkalic pegmatite system that has 3% zircon, just very high ore grade heavy rare earths and yttrium, except the dikes are not very wide. They're only a couple meters wide. So it's not very important economically, but it's important petrogenetically. And the age of that dike all of those dikes we dated, they're all exactly the same age at 420 million years. Now that stuff was done 15 years ago. And I just never wrote about it or talked about it because I just thought it was so simple of an idea. What is the thermal regime in which magma systems fractionate? Just nobody really thought about it, I guess, because it's so simple. But it's the neat thing, it's modelable. You can take and modify that. You can modify the thermal gradient in K-Ware, heat 3D. It's easy to do. And actually here, I got the idea from one of my colleagues that uses heat 3D for teaching of these types of things.
Yeah. And it's possible to model the recharge events in the chamber?
It's not easy to do that in a dynamic way, but you can always do it just in an incremental way. It does have some parameters. The new software for this actually is much more dynamic than the one that I had. And so it is possible. So for example, as you know, for how does the Bushveld grow by double diffusive convection, multiple injections of recharge into a magma, as you know, and how those melts mix, saturate. That was one of the mechanisms for figuring out how chromite saturation happens, maybe even magnetite saturation. Anyway, these things are also modelable because if you know what the new melt system is in terms of temperature, all you do is you reset it and then let it run again. It's just recognizing each one of them to optimize the system. Maybe I should give a workshop sometime on using 3D instead. But it's downloadable under K-Ware, and then you send an email off. He's a really smart guy, a very famous volcanologist at Johnson Space Laboratory or Johnson Jet Propulsion Laboratory, and obviously he does geologic research for, in essence, Mars and moon missions and Mars and so on. Extremely bright guy, and he had done this like 20 years ago. I haven't interacted with him recently, but definitely people have used Heat 3D for all sorts of things. And obviously it's derivative from other people modeling other types of thermal anomalies from blast furnaces and so on. He just took it, modified it all so that we can model different types of geologic systems.
Dave, I have a question.
Yeah.
The metals are always coming from the source, or it is a requirement that we need to have a source enriched in metals?
That's a very good question, Martin. I think for some systems, I think that probably is the case. However, in many systems, I do not think it's the case. So for tin, geochemical heritage, like Byrne-Lehman had shown, are almost always associated with paraluminous magmas that have S-type characteristic of supercrustal melting and so on. Couple with that, with just taking a look at normal crustal rock values versus sediment compositions, and you can see that a lot of shales are enriched in tin by about 3 to 4 times than a normal felsic rock or even mafic rock. So the amount of tin in a normal mafic basalt from the mantle is about 1 ppm. A felsic rock is maybe 3, but many sedimentary rocks, shales, and so on are about 10. And therefore, obviously, if you have that advantage 3 times more, then it's probable that the source is a consideration. I think it's a consideration as well for tungsten deposits, although there's lots of different reasons, different systems that can have higher tungsten. But then systems that have lithium, cesium, tantalum, we know those are all from sediments that are eroded from volcanic rocks that are enriched. We know that by recycling into the subduction zones from accretionary wedges and so on. So again, for those elements, I think it's important. For molybdenum, I think it's important as well to some degree, although we see molybdenum in all sorts of porphyry deposits, and then obviously the amount of molybdenum in any system will be a function then of fractionation. However, if we take a look at, and obviously those are oxidized magmatic systems, i.e. because fractionation of things like ferromagnesians and ilmenites will pull out molybdenum, sometimes tungsten in those. Now, I don't know that much about those partitioning reactions, but I do know it's an issue. So those are oxidized, fractionating magmatic systems that relate to amongst molybdenum endowment. However, when we take a look at that, and we take a look at something we do know about that are enriched in the crust and the crustal protolith, is like lead. And we know that, it's very well known. Laura and I have used lead isotopes a lot. The issue is that we know lead is enriched in the crust from very primordial fractionations all the way through every other type of fractionation through time, such that we have higher uranium, higher mu values in the crust. And therefore, when we take a look at lead isotopes in molybdenum-rich systems, we do start seeing some sort of crustal signature. No matter what they are, there's a slight crustal signature in there. Now, how much is that important to a molybdenum endowment? I'm not exactly sure, but I do know that they're showing more crustal signatures. And any crustal signature within an arc system that has magma after magma after magma is telling you that there's something in there, because the residence time of the rocks that are part of the crust are not very long. So any sort of radiogenic lead in those systems must be from some pre-existing crustal source. So I do think there is. And if you look at it in mass balance terms, there probably is as well. However, we don't know, even in mature arc systems like the Andes, we don't really know that much about that deeper crustal keel that these melt systems migrate, react, move through, and assimilate. So it's a good question. It's just, it's a hard question. However, saying that, we now are using molybdenum isotopes. And this is how we're going to solve this. Obviously, some of the great people out there doing this now, like Ryan and so on, and I think Laura's starting to work in this area. These are areas where metal isotopes are really going to help us. So that's where I think the future is for figuring out endowments within those specific things.
Perfect. Thank you, David. So clear. Thank you for the presentation.
You are welcome. Anyway, I should let everybody go. It's supper time or vino time in Argentina. It was nice seeing you again. Laura, thanks for the invitation. And yeah, we should do this again sometime. Maybe I'll invite you here for our SEG. Hey, Alan?
Yes, for sure. She will receive a request from me anytime soon.
See, this is the way it works, Laura.
Excellent.
Anyway,
thank you very much, Dave.
And so it's a win after all.
Yes, thank you very much for helping us.
Yeah, well, it was great.
Yeah.
Yeah, well, it's an easy one. It's an easy fix, and anything where we can learn something about technology is all good.
Of course.
And having backup and Skype is always helpful too. So very good.
That's
Have a
true.
great night, and
Thank you
we'll
very
see
much.
you again soon. All the best to you guys in your research, and happy holidays, Merry Christmas, whatever.
You too.
Thank
Dave.
you.
Thank you
Bye-bye.
very
You
much.
too, David.
Have a good
Thank
end
you
year.
very much.
Bye-bye.
Bye-bye.
I thank you.
Bye. Thank you.
Thank you, Dave.